introduction. Pleasure to be here today and speaking to you about a concept we are thinking of for managing flights in altitudes above flight level 660, so I think that fits quite well for the topic of this symposium. So let me first start with, I think, a quick overview which shouldn't surprise you as much. Of course, when we're thinking about the different altitudes we're talking about, there's a quite different perception maybe from the space community and the aviation community. So when we are talking about aviation, of course, everybody's thinking about operation basically below 20 kilometers or an altitude of 60,000 feet. Above 100 kilometers roughly, we know there is no delimitation of space. Really, we talk about space, and in there between you might find some people arguing about near space, other people arguing about higher airspace. It's basically the same. We are talking roughly about an altitude range between 20 and 100 kilometers here, and this is actually where, let's say, controlled airspace that we just have learned is ending at about 66,000 feet. But we're not yet in space. So this is altitude regime we are talking about also for a lot of applications in the hypersonic field. So now we are facing some challenges in this area which has been vastly unused in the past. But there are several concepts now addressing this range of altitudes. It actually ranges from starting from the left, from high altitude platforms. You have a lot of concepts actually, and there has been quite a nice introduction at the Hubs for ESA conference at the beginning of this year about how many different concepts there are for having high altitude platforms, starting with fixed wing platforms like the Abu Sapphire. Here on the pictures you can also see some platforms which have been let's say, not continued in its development. Nevertheless, there are multiple new ones in the making. And you have also the high altitude balloons and airships, Gugaloon. There are projects here for Stratobus. A lot of ideas of actually using this high airspace in an altitude range, basically between, I would say, 15 kilometers to up to 22 or even higher altitudes. As long as you can navigate with something which gives you lift, if it's fixed wings or if it's also balloon style. On the other hand, we have what we call suborbital spaceflight. Giovanni has just introduced us to, let's say, the definitions of suborbital. There are ideas, everybody might will know Spaceship Two approach and also the Blue Origin approach, but we are talking about point-to-point suborbital transportation and other means of ideas for using these ranges in a suborbital way. And we have the classical launcher business, bringing satellites into space, also transferring through these areas. So if we consider all those different, let's say, options in the near space region, we might find the need to categorize them a bit. So if you try to categorize them, you first of all have the transit users. This is operations that transit the airspace vertically, and that includes basically launch and re-entry operations. On the other hand, we have the persistent users. Those are the high altitude platforms who want to stay over a certain place, maybe for a long duration of time. So they are quite slow, of course. They tend to maintain their position, completely different kind of way. And then we have the point-to-point users, actually going from A to B, concepts which are using hypersonic transportation, as an example. So with this in mind, the question is, what kind of conditions are we facing in this region? So usually if we have aircraft which are operating in these kind of altitudes, they have to transit first through controlled airspace, so that in principle would us allow to provide service without new mandates, because we already have, let's say, guided them and mandated our service to them. In this area, of course, we are free from obstructions and terrain. Besides, we put any kind of restricted airspace in that part. Currently quite uncongested, and even with all the concepts coming, I think we're talking about a more uncongested way than if you're somewhere near an airport, for example. And we usually have aircrafts or vehicles which are very closely monitored by a ground operator. So you have a lot of data actually available on the ground as operational parameters from those vehicles. So shared information on position, altitude, trajectory we can use maybe also for collision avoidance and also for planning conflict-free routes. With that in mind, we have taken a look at what kind of conceptual approach could we go for managing traffic in this area. So first of all, the basic requirement is that we have a safe operation. So we have to maintain separation between all vehicles at all times. We have to cope with large speed differences, as I told you. So we have hypersonic and space launchers at the same time as we have stationary objects or very slow moving objects. So with that in mind, tactical control is not an option. So you cannot really tactically control that and deviate and try to give them commands to avoid a certain other vehicle. So maintaining separation is becoming a strategic effort. And with that, we come to the idea to how to plan these operations to be conflict-free. Therefore, we choose an approach of strategic separation. So the operations is going to be planned ahead in time to remain conflict-free. We consider the different types of operation, from short duration high-speed flights where we have some time uncertainties like launch time or something like that, as well as long duration flights over relevant areas of interest. Then we come up with entering this into something which we could call a near-space operation management system, which doesn't have to be seen as, let's say, a tool which is having this name, but just maybe a concept or a system which is getting integrated in the current air traffic management system. So this kind of near space operation management system then makes a route and schedule which is approved as a conflict-free. So you plan your route, you make sure that the planning is conflict-free for other plannings. You augment this later on by tactical monitoring, so you have your planning, but there might be deviations, so you have to make sure that you are able to track these kind of modifications. Mission assurance is provided for long-term planning, so if you're, for example, planning a rocket launch, you want to make sure that you have this planning to be quite stable. And we have to make sure that we have this interaction going on also with airspace below flight level 660 and also with Earth orbit, so if we are talking about launches actually, we want to make sure that space traffic management is considered as well. So by doing that, we think not only about 4D trajectories here, but more like 4D operating zones. So the concept makes use of, or is taking into account the uncertainty of aircraft position or vehicle position over time. So the route is modeled as an operating zone rather than just a 4D route. Which is a four-dimensional shape and volume which might change over time. It varies based upon performance characteristics and also mission design. So based on your mission, you might have also, let's say, thinking about a stationary object like a high-altitude platform, you might want to be at a certain place over a period of time and then go to a second place over a period of time. And you could, let's say, get this into the system. Operating zone planning. So this is just what I said, changing over time is part of the flight planning process. And you will also incur certain changes during the operation by external platforms, factors like weather, of course. You have to encompass equipment failures if they happen. But also your mission requirements might change. And there also might be some deconflicting measures actually in the planning process. So this should be covered by the system as well. The monitoring task then is very important to ensure the safety during operation. Monitoring vehicles along their routes and also their schedules, that you have this conflict-free ensured, and that you have a mechanism in place that actually is encompassing the request for changing your trajectories. As long as you're not being in any kind of additional conflict, you should be free to fly where you want to fly. These kind of in-flight modifications are very important, and usually it's really just to make sure that you have, let's say, a process running beneath which would give you a warning if you are encountering certain, let's say, conflicts or getting in touch with other possible flight paths. So there's a concept which is called flight-centric ATM. And air traffic control, which can help us actually to apply to this. This is a concept which is already being developed for high airspace operation. And this can be probably extended towards the concept we are talking about here. So what kind of infrastructure and data provision do we need? The advantages, as I said, we are talking about vehicles which are under very close control by ground stations. So we can actually utilize ground operator infrastructure. We can then, of course, use the vehicle state information and the planning information and try to share these kind of data using system-wide information management as one of the core sources to spread information back and forth throughout the air traffic management system. To make sure that we have a surveillance and to know where the aircraft and the vehicles are, as we mentioned, we can use several sources of data, and the multi-source surveillance approach here, I think, is essential. First of all, like we said, we have tracking data which can be provided by the operators of the vehicle, as well as we have data which we can receive, for example, by a space-based ADS-B system or something similar, which we can then also feed into the system-wide information management approach to gather these kind of data, aggregate these kind of data via Fusion service, for example, and provide them to whatever entity is making use of this kind of near-space operation management and monitoring. Then at the end, the interfacing aspects. As I mentioned, we have to make sure that if we are coming from controlled airspace into the near-space regime, we have to make sure that the system is capable actually to interface with, let's say, what we call today regular ATM, or making it a part of the air traffic management system, so that we have the transits between those airspaces are covered, that we have considered the flight planning requirements for both domains, flight plan status information, sharing again via SWIM, and maybe also just adapting the existing data exchange formats which are there, which have the possibility to be adapted in future releases, like the flight information exchange model, the FixM, to make sure that we adapt these kind of information and put them into our current air traffic management functionalities. On the other hand, we need to make sure that we are able to interface with space traffic management. So space traffic management, considering on-orbit management of objects and debris on their trajectories, on their orbital trajectories. So based on the concept of flight we have for a hypersonic flight, for example, which might cross altitudes, I mean, it's still suborbital, it might be hypersonic at certain times, even if you go above 200 kilometers of altitude. So we have concepts which are using these kind of altitudes. Then we have to make sure that we are not only free of any kind of conflicts with air traffic, but also free of conflict with possible space objects, controlled or uncontrolled objects, because we want to make sure that our flight is safe. These kind of position and status updates also for re-entering vehicles are essential, then back and forth between STM and ATM, and have, again, a possibility to exchange these kind of information in real-time capable systems using appropriate standards which are out there already. So, crossing now towards the end of my presentation, I want to check some commonalities between air traffic management and space traffic management here. So, on the one hand, we have what ITU is doing for spectrum allocation. We can have a look at that, considering what's going on in the space traffic management world. For ITU, they are responsible within their principles to avoid harmful interference between frequencies, to ensure efficient, rational, cost-effective utilization within the frequency spectrum, develop procedures that facilitate the access to the resources which are limited but which should be available, and establish global standards on, let's say, how to assure these kind of required performance and interoperability aspects. On the other hand, if we look towards ICAO and air traffic management, there we have as one of the most important principles the prevention of collisions, expedite, maintain orderly flow. We want to provide advice and information for safe and efficient conduct of flight, and also to establish global standards, all about safe, efficient, secure, economically, but also environmental friendly operations. So if we combine those principles of both domains into what we think about our near-space operations, then we can, let's say, combine them to, let's say, near-space operational principles, which would mean to avoid harmful interference, prevent collisions between operators, provide advice and information which are useful for safety and also efficiency in conducting our flights, develop procedures to make sure that we all have access to the resources, expedite, maintain orderly flow of air traffic, of course, and also establish the global performance, interoperability, quality, safe, efficient, secure, economically sustainable, but also environmental operating environment between 20 kilometers and 100. So, by saying that, just coming to my summary, we have learned there is a major challenge in organizing traffic in this altitude regime through the three types of users: transit, persistent, and point-to-point. The conceptual approach we are currently looking at is making use of strategic separation, which, by the way, when we're talking about 4D operating zones, is quite adapting what we have out there as the trajectory-based operational procedures, which is part of CESAR, by the way, when we're referring to that. We think that we can make use of existing standards like system-wide information management. We have to make use of information which is available at the operator side, but also have to find some independent means of information and surveillance. And at the end, the service we would like to provide should, we think, not require new mandates, but a merge of principles between space traffic management, air traffic management could be the trick to actually get those aspects to be fused. So, with saying that, I would just like to refer to, I put together these slides together with my colleague Bruce Stilwell from the US as part also of a paper we did at the ISC conference last year in Bremen at the ISC conference, so you can find more details about what I just talked about and our ideas on that in this paper. So feel free to have a look at that. Very happy to be here today, and thank you for listening.
Thank you very much. We do have time for one question or two, and in case there is some further curiosities to satisfy. I see there is none, and my Swiss watch is happy. Thank you very much, Sven.